It is my pleasure to introduce Dave Armstrong from Advantest. Uh, his capacity, he's the Director of Business Development, works with customers to find and deliver creative solutions to some really tough test challenges. In addition, Dave is currently the chairman of the test working group of the Heterogeneous Integration Roadmap. Prior to joining Advantest, Dave spent over 2 decades at HP Agilent in the IC test group as the principal engineer, and he's worked with a variety of different companies throughout the industry prior to that. Dave received degrees in electrical, computer, and environmental engineering from the University of Michigan. So it is my great pleasure to introduce Dave Armstrong, who will talk about our best known methods for testing of high power ICs. All yours, Dave.
Thank you, Ira. So best known methods is my term for things we've learned along our life's paths, and wanted to share a little bit more detail on who I am and what has been my life path. First off, degrees in mid-70s from Michigan, 3 of them. Note that they really align fairly well with the topics we're working with. My first company I worked for was TRW Systems, Redondo Beach, and there I actually designed ICs. Sorry for the poor quality of this picture. I took it myself, but note something unusual on this picture. You might note some mid-die bonds. This was unheard of in high reliability device development back then, but I did the calculation and it turned out that the power bus here needed to be wider than it was long in order to meet our design goals. So I learned very soon that power supply and cooling actually went together, because once we put this bond in and had lower noise on the die, we were able to reduce the power supply voltage to the part, which meant less cooling. It really is a tight loop going around and around, and this learning keeps repeating itself throughout my career. So my career actually involved a number of companies and a number of roadmap committees. And the nice thing about this career is it allowed me to work with a bunch of experts from a lot of different companies out there. Some of them very leading edge, some of them doing some incredible things. And together, we learned the tricks of the trade, if you will. So today I want to try and document those tricks, these best known methods. And obviously, there will be better known methods as we move forward. So what is the problem statement? What are we really trying to do? We have a device that may have a bunch of cores in it. 4 is a low number these days, but let's just use 4 as an example. We have a DUT board that has capacitors on it, a bunch of different types of capacitors, and we have cables connecting to a power supply. So our challenge is, what type of test power supply configuration, cooling configuration do I need? How do I put this all together? How do I control it, bring it up so I don't, power on can be a big, big problem for a lot of these. And by the way, what's my control circuitry to my active control system, my thermal control system? And I think Adam's going to talk next about how do I generate the vectors so that I don't blow things away with our scan patterns. So actually the digital interface can be part of our thermal problem. And as Arun has already said, let's not blow up, let's not burn some probes. That's a very expensive thing to do. So I'm going to talk about all these topics and things I've learned on my career path. So real world is messy. Here's a real world plot of power consumption or current consumption, voltage levels, temperature, on-die temperatures, as it runs through a sequence of tests. What do we see here? Well, we've already said scan test is probably the high current consumer. But note that the scan test has spikes in it, a bunch of high spikes. Note also that the power or the voltage to the die is not necessarily staying real constant. So one of the things we will talk about later on is the need to have additional capacity, both in the thermal and in the power delivery path, in order to be able to flatten out at least the voltage spikes. The thermal spikes, well, I have some tricks there too. So what about thermal capacity? Well, thermal is dictated by power, not just current. So if we look at this sequence, this is fairly well controlled, but you have multiple different power levels as you go through this. And again, the big challenge is the thermal spikes, which are occurring during the scan test, and being able to handle this as I size my cooling system appropriately. If I were to just size it based on power consumption, you'd say, well, it's the duty cycle times the voltage times the max current. But that won't get you where you need to go. You need the added capacity for this. I actually sat down with our thermal guys in the handler group and said, help me understand, can I put together an equation for this? It's not easy. The best I can tell you is get with your thermal company early and make sure you design a solution. And that solution, by the way, may involve TIMs and cooling the socket, cooling the probe, could involve a lot of things. Ken and Arun have already talked or touched on active thermal control methodologies. I'm going to touch on it as well. So let's talk about power supply first. I thought might liven it up with a little bit with an analogy. Let's talk about hoses. So if we have three big hoses now feeding a funnel, this is my bottleneck, and then I have three smaller hoses watering my garden. If one of the hoses over here gets a kink in it and doesn't do much, guess what? You're going to have a lot of water flowing through the other hoses. So one path will get more current than the others, and it could actually explode. Well, how do you want to solve this? Well, if you have these three high power hoses over here, you feed them through three funnels with control valves. Now, if you have one of the hoses getting a kink, the other hoses, yeah, will take more water, will feed more water, I guess, if you need it to. But the reality is the control valves over here are going to constrain the amount of water you get, and you're not going to get a damaged hose. So if I map this back to a power distribution network, here I may have three individual supply channels going through individual cables of some nature. And you may want to, in the past, we've always connected them together on the DUT board with a bunch of capacitance, bulk and high frequency capacitance, and then drive through multiple probes to the core, where once again, the power is connected to each other. Well, there's lots of different ideas here. One is you could actually connect the supplies together back here on the module. This is, in my opinion, a terrible approach. You risk blowing out the cables. If you need more current, you may actually blow a cable, and you certainly risk blowing out the probes. Merging on the DUT board is certainly more common. Here again, though, your current can shift and go where you don't want it to go if one of your contact resistance starts rising. I put this third one on here and actually got pushed back internally. This, in my opinion, is by far the worst case scenario, because if you have a power rail on your device and on your DUT board and you have a contact problem, guess what? Your current flow will flow through the contacts that are still there, and it will come down on your core or on your device to where it's needed. As a result, you would have too high a current on the die, on the power rail, and you could actually have electromigration in addition to blowing up your part. So that's a bad thing to do. Don't want to merge on your DUT board and on your device both, or you could end up hurting parts. Well, what's the right solution? In my opinion, and this is where the industry is trending, towards individual power planes, each one feeding one or more probes, and then the flow going in a coherent sense onto the die. So the only good answer, in my opinion, for these kiloamp parts is you have to merge on the die and on the die only.
So, Dave, a question. I mean, so sometimes the power plant is merged in the package, and when you're testing the device at wafer, it might not have a common bus. Is that a challenge to this approach?
No, I think that's the opportunity, because there, if that wafer, you don't have the common bus, then you have to drive each core individually. Then you just have to make sure that your duct board is set up the same way.
Okay.
So the next thing you need to realize is that the sense pins are where the specifications are guaranteed by the tester. If you don't sense on the die, you're not guaranteeing within the specifications of your tester what the that you're getting the right voltage with the right accuracy. With the supply voltages dropping, this is becoming more and more critical. Certainly, dividing up your power leads, which may be forced on you because of the packaging scenario and the probing scenario, is really the right thing to do. You need to definitely have these senses. One thing that I've done with a few customers is we've actually, if you have a single power rail externally, you can switch the sense lines around to get sense from core 1, core 2, core 3, and then you get more accurate voltage on the cores you're actually testing at that point in time. As Arun alluded to, you don't necessarily test all your high power cores together, so why have your sensing done together? Why not use sense that's directly associated with the core of interest? So this is what a burnt probe looks like. I have 3 slides here that talk about burnt probes. As Arun said, this is not a cheap problem. And note that we say burnt probe, but it's really burning a bunch of probes. What happens here is you might get one probe that gets overloaded, and then it will burn out, and then some adjacent probes will then get overloaded. So it's really an avalanche situation. So how do we avoid this? This is really important. You need to ensure that your probe current is well controlled. Segmenting the power supplies to the subcircuit of interest, maybe a core, I call it a core, is really valuable. It helps you manage it. Now, in addition to that, if you have sensing for each one of your channels, each channel can individually change its Kelvin voltage to keep the current balanced. The next thing you want to do is you want to make sure that you have the smarts in your supply to make sure that that current is balanced, because you may have one channel, which really gets out of control. Well, guess what? Now your current's going to need to be divided, and the current will come from the path of least resistance. So now you're going to have extra current here, and you're not going to have it here because you still have a contact resistance problem here. So your supply needs to be really smart to monitor and control the current on a per channel basis to make sure you never exceed the CCC of the probe that you're using. This is probably the most important thing you can do to avoid probe burn, in my personal opinion. Oh, by the way, I also mentioned up here, preventative maintenance. Monitor your contact resistance on a per power plane basis. Now, you've set yourself up for success, and you got to turn on your supplies. How do you do that? Well, you got multiple cores here. Well, you don't want to just bring up all the supplies together, all the cores from 0 to 1 volt simultaneously, because you could have core-to-core shorts. You could have shorts you don't know about. And you actually could have one supply growing faster than the other supply, which could cause current flow from one core to the other and that you don't know about. Best known method here, in my opinion, is to walk slowly all your core voltages in lockstep and check your current consumption for each core in lockstep and getting up in lockstep. And if you see something going out of control, stop. That will preserve your probes, and that will preserve your die. Now, even with the best control along the way, things can get out of control. So your supply needs to have methodologies for handling it. So if you bring up your supply, the first thing you're going to find is that you're going to get a current spike. And very often in the past, we just said, well, let's just wait for a while before we start looking at current. Well, that current spike could be just because you're charging an uncharged capacitor. It could also be because you're driving a device that's shorted or cores are shorted. So you want to make sure that this current influx is controlled and understood, because otherwise you're going to have problems. The problems can be the charge, the influx going to the core, or even hurting your cables or other things. Once you're up, you can certainly see clamp situations. Clamp current here is shown with the dotted blue line. Obviously, you need a fast responding clamp so that you don't get out of control. Let's move on. So the next one is foldback time. I was tempted to talk about thermal runaway. Thermal runaway is where the current gets too high, and all of a sudden the temperature of the die gets too hot, and that causes more lower diode voltages and more current. So thermal runaway is caught by a fast clamp time. That's where you really get it. Foldback is when things really get out of control. Now note that you have various times in your clamp in this drawing I drew, and this is actually a real world drawing. And these may not be long enough to trigger a foldback condition. Well, foldback occurs when you have clamping for too long a time. And what do you want to do when you get a clamp? You certainly want to fold back all the supplies for the core you're testing, perhaps the die you're testing. But equally important, you want to make sure you don't fold back all the supplies for another site you're testing. So control, keyword all the way through this is control. And the final control is when you want to fold back, you want to make sure that you can quickly discharge your bulk capacitors to make sure they aren't charged. Why? To avoid arcing. One of the old tests I used to do when customers say, "Hey, I got I'm blowing up probes." I said, "Okay, well let's try on your test. Now let's turn off the lights, and now let's raise your probe. Do you see anything?" Bingo, arcing. So now let's talk. Go ahead.
Sorry, Dave. On probe resistance, I know that years ago that the test engineer had to manually run those kind of tests before running the other tests. Is there anything new in terms of automation, or how does the tester measure it is one of the questions the audience was asking.
So probe resistance, I think when you divide up your supply to sub-circuits, subdomains, now all of a sudden you can get probe contact resistance, and while you're running the test. So inline probe contact resistance is still, in my opinion, hard. We're improving it. I think we're improving it significantly, but you may also need to do an offline metallized wafer test as well.
Okay. And then a question on the foldback and the clamp. Is it fast enough so you can shut down the thermal runaway, or it's just going to avoid extra damage, or can you use it to throttle the thermal runaway? Is it all or nothing, and how fast is it?
So to avoid thermal runaway is really the clamp time, in my opinion. The foldback occurs here. You're protecting the probes. So here, I believe it's fast enough to protect the probes, and here I'm hoping that we're fast enough to avoid the thermal runaway. Notice I'm using what I call weasel words. Obviously, the proof is in the pudding, and the user assigns the foldback time. I don't. We work really hard to get our clamp time in the hundreds of microsecond range. And believe me, there's a lot of people that are really excited that we're in this range. So hopefully we're going to avoid thermal runaway. No guarantees. Your mileage may vary.
Thank you.
Power distribution. I've always been surprised or kept in the back of my mind how a power distribution network really looks a lot like a transmission line. And a transmission line, you're trying to get broadband delivery of a wideband high-speed I/O signal. And guess what? Your power network, distribution network, you want to do the exact same thing. You will have different types of capacitors along the way. You're going to want to have a high-frequency ceramic capacitor at the end, and you're going to want to have a bunch of bulk capacitance very early on. When designing a DUT board, you want to select the right capacitors in the right quantities in the right locations. Too little is bad. Too much can be worse. You want just right. Well, how do you get just right? I started going off into how you get just right and finally decided just right is determined by working with your vendor. We have a very nice tool that helps you determine just right temperature, just right capacitance amount that you need for your DUT board. Well, then the question comes, well, what capacitors do I choose? Well, for these high current, high power devices, you typically end up with a fairly large amount of capacitance. In fact, in my opinion, for almost any DUT board, you can't get by without any capacitance. You have to have capacitance because why? It's because the capacitor is what powers your device when your inductor here is limiting the response time of the power of the device power supply. So from my experience, tantalum capacitors is a very, very good choice, if not the best choice for bulk capacitors. Ceramic capacitors certainly provide a very high frequency solution because their ESR is lower. So tantalum capacitors, why? Because they have wider temperature range. In fact, I ran into this problem just last week. Customer was having a problem where he was doing at temperature testing and his part was operating very, very funny. What we determined is that the thermal conductivity out the probes was enough that he was causing his ceramic capacitors to go into a range where they weren't getting near the capacitance that they expected. And all of a sudden his part was failing. Ceramic capacitors have some very nasty temperature problems. Tantalum capacitors are very well understood and controlled in that regard, and they actually are lower, higher capacitance per area and lower cost per microfarad. When Ira saw the original version of this, he said, well, tell me what's wrong with ceramic capacitors. Well, one thing that people may point to is that their ESR is not as good at high frequency. Well, you want to use them at low frequency. And by the way, their equivalent series resistance at low frequency is better than ceramic capacitors. But that may be perceived as a disadvantage. Probably the big disadvantage is they are polarized. If you ever expect your supply to spike negative, you could permanently damage your capacitor array. So don't use them if you ever expect any negative going voltage spikes. In all the testers I've ever worked on, this is never a problem. Tantalum capacitors have always been used with very good results. So active thermal control. Here I think I can help both Arun and Ken learn a few things. Wish we had a panel, it would be fun. But anyway, Advantest has and manufactures a bunch of high performing thermal systems. And these are based on dual fluid. And as people have said, changing the fluid temperature is very slow and involves challenges. So thermal time constraints are a concern and a problem. It's in the milliseconds, as has been mentioned. One thing you may want to think about, by the way, is that conductivity may mean that you want to cool the contactor or the probe. But what we're talking about today is the power control and the ATC control, which comes out of the tester. There's three basic ways to doing this: diodes, power following, and what I'm calling is power anticipating or power predicting. So let's talk about all three of these. In the beginning, people used a single thermal diode. That has massive problems because you got different thermal signatures in different parts of the device. Today, anybody who's doing this has multiple diodes around their device, and they switch to the various diodes on the fly. And there's even the smarter techniques like Ken alluded to, where you might want to take the average temperature across some dies or the maximum part, or switch which diode you use or which temperature sensor on the fly as you're running the test. That's a better solution. Don't use one diode, please. Power following has been around forever also. This is a misnomer actually, because the way people have been implementing it is by current feedback. They put a resistor in the flow, they feed this back to the ATC, and then they can say, hey, what's my current to my device? Well, the device is a very complex part here, and your voltage levels are jumping all over the place. So that's not very good anymore. So here, I want to alert you that there is a better answer and to power following, where now if we control or drive the cores with individual supplies, newer supplies can actually monitor not just the current, but the power that's being provided on each one of these channels. And we can even sum the power together and feed it back to the ATC. And one more step, we can actually switch around which cores are feeding the ATC under program control as we're running the test. So power following all of a sudden, I think, is getting a second wind and is certainly a better solution than the diode approach. So let me talk about what I think is the ultimate one, which is one that Advantest actually patented almost a decade ago, which is power predicting. In a power predicting sense, and by the way, Arun, I think you and I are going to want to talk about this, we can identify a test suite. And this test suite may be a high power consuming test suite, or could be a cache resident test that has its own power signature. So I can pre-trigger in the pattern. I can predict when that power is going to peak. And I can actually have in the background a power profile. And that's actually what's in the patent here. We talk about the profile for the thermal signature for this test. So I can actually change the target temperature on the fly because the tester knows when that test is starting. And it also knows what the power profile is for that test, even if I'm not monitoring it myself. So what does that allow me to do? It allows me to tell the thermal system to cool down early, and then the power transient is actually more of a plus or minus some degree C and not just a plus degree C. So this keeps the device from overheating and from thermal runaway. So this is something that uniquely Advantest can provide with, thanks to our patent. So questions? You look like you were going to say something. Let me talk about the BKMs that I have here talked about here, and maybe some I haven't talked about. So first and foremost, you need to plan ahead. You need to get the right tester, handlers, probers, probes, thermal contactors, capacitors. You need to think everything through carefully to make sure that you're set up for success. You need to talk about maximum, or think carefully about maximum current draw, including power-aware patterns. I think we're going to talk about that next, and making sure that your power supply is well configured. Anna's going to talk about this. You need to talk to your cooling experts, and you got to look past voltage, max voltage times max current times duty cycle, and you need to add capacity, not just only in your thermal system, but in your power delivery system, to make sure that you can handle the transients that you're going to see during your scan test. DUT boards need a bulk of attention, really a lot of attention. Capacitors I've already talked about. Subcircuits need their own supply path, which needs not just supply path, but sense feedback. And the sense needs to be to the current forcing circuits for that sense, for that portion of the circuit. This is actually something I saw emphasized in a recent Teradyne presentation. If you have extra supplies, use them. Don't let them sit there idle. If you got a 256 amp supply and you got 56 amps you don't need, apply them to other channels. You're going to get a lower effective driving impedance, faster settling time, lower noise, and a better test. You might want.
Dave, do you meant number of tester channels? You said 256 amps. You meant 256 channels, did you not?
If your DPS is a 256 amp, that's just one that I'm using a lot these days, and you only need 200 amps for your part, don't let the other 56 amps go to waste. That's all. And certainly you need to look at what probes and pogos you're using. There are a lot of advancements going on here. And, there's another conference IRA leads that talks a lot about this. And I think it's a good thing to think about early on. And finally, you're not done. You got to make the test program effectively. You need to carefully power up your supplies so that you don't have draws that you don't control and understand. To make sure that your patterns are correctly done in the correct way to minimize the power. And you may want to space out the patterns, as I think Arun mentioned, to minimize the power dissipation as you're running the test. So a lot of these things are best known methods that a lot of us are talking about, but frankly, if you don't worry about them, you're not going to get to a kiloamp. And there's a lot of people I'm talking about these days that are going there. That's it. Any other?
So, yep, let me just start the poll here for Dave, and if people could take a minute to fill that in. Question was the power predicting, if you're starting the cooling earlier, might you actually have a test escape where the tests prior to where you need the additional cooling are actually run cooler than they're supposed to? I mean, so could you get caught with you got to start it too soon and miss something there?
I think that's a very insightful question, and yes, possibly you will. However, I haven't seen thermal control systems being able to respond that quickly. So my guess is, the lower temperature you might get before you expect it is very small. That's from my own personal experience, but you may want to talk to your thermal company to confirm that.
And there's a lot of questions from on load boards, and as you and I both know, those could be a whole conference in themselves. Designing them the right way, we actually have a track about that at Test Connects too. So there's a lot of challenges in doing it right, and so it's really important that you rely on the experience of the apps engineers to help guide that. The question, it seems like a lot of the design rules we have now are probably 180 degrees from design rules from, let's say, 15 years ago. And is that based upon the parts are more challenging, or we've learned more? Because obviously the physics of what we're doing is the same. It hasn't changed in that time, but some of the rules of thumb and what people are doing are different than we used to do them.
So I would say there's 2 or 3 parameters here. One is certainly we've learned a lot. Secondly, I think the tool set, the consumables, have come a long way. And thirdly, I think the parts have become much more challenging and much more expensive, and we can afford to do more things that we couldn't do in the past. So a best known method today is for today's parts, and yesterday is for yesterday's.
Great. Well, thank you, Dave. Want to once again thank our sponsors who made this event not only possible, but made it free for everybody to attend: Advantest, Amcor, Indium, FormFactor, and Nidec SVTCL. And Advantest, once again, is a global leader in the ATE industry with nanotechnology products supporting leading edge with a diverse workforce and eco-friendly policies. Amcor is driven in the areas of technology, quality, and service in terms of advanced packaging, high quality execution, and a complete array of services from design and test through drop ship with a manufacturing footprint throughout the world. And Indium, with premier assembly materials designer and manufacturer, thermal interface materials, solders, paste fluxes, and materials and compounds. So when you have an opportunity, please thank all of our sponsors and encourage them to help drive future events, but we're very thankful for their support of Too Hot to Test. And I will wish everybody a good rest of your day. Thank you for joining us.